All right, good afternoon, everyone. Welcome to ISP's virtual bootcamp webinar. Today's topic is experimental evaluation of GFRP bars as reinforcement for cast-in-place bridge decks, low cycle fatigue study, presented by Zeyn Uzman. I do want to inform everyone today, I know this was marketed as a 1-hour presentation. It's actually a 2-hour presentation. So you're welcome to stay on for the full time if your schedule allows. My name is Ariana. I'm the education specialist with ISPE. So if you have any questions about today's webinar or any of our other programs, please feel free to reach out to me. I just have a few more quick announcements before we get started. We're not going to be having handouts for this presentation, but you can access the link to the quiz on the same webpage as the past few weeks. You should have received a link to that webpage in your confirmation email from this morning. Please be sure to complete the quiz by this Friday, and I'll get you your PDA certificates either on Friday or next Monday. If you have any questions for Zeyn at any time during the presentation, please go ahead and type it in the questions box on your taskbar. I'll go ahead and read those out loud at the end of the presentation. So with that, I'll go ahead and hand it over to Zeyn.
Thank you, Ariana. My name is Zeyn Uzman, and what I'm going to be presenting on today is a study that was done at Villanova University by Angela Russo and her advisor with Dr. Joseph Yost. And I also helped her with it, and I did a continuation of this study afterwards when I was working on my PhD at Villanova. With that, we're just going to go ahead and get started with the presentation. We should be not the full 2 hours, but we'll see how we shake out here. All right, let's do an overview of the presentation. I'm going to talk about why are we doing this, talk a little bit about what fiber reinforced polymers are, do some slides on the design of bridge decks, show some of the sample details, how we set up our testing, the test results, and the conclusions. So why are we looking at doing this study? As of August of 2007, there were over 6,100 structurally deficient bridges in the United States, and a lot of this has to do with corrosion of the reinforcing in the concrete. In the areas where there's a lot of chlorides used for de-icing salts, you get cracking in the concrete decks, and the water with the chlorides in it infiltrates into the concrete and starts to corrode the reinforcing bars. And you get spalling, deterioration, loss of section. And in these pictures here, you can see typically what happens. Now, there has been the advent of going with epoxy-coated rebar, but that has not eliminated the corrosion in the steel of the reinforcing. So, possible solutions that are currently on the market now are galvanizing the reinforcing bars. You can do an electrostatic spray, fusion powder, resin coating, polymer impregnated concrete, epoxy coated rebar, or look at using fiber reinforced polymer rebars. Primarily, the epoxy coated reinforcing bars and the galvanized coatings are the two most commonly used in the United States at this time. So what is fiber reinforced polymers? It's a composite material made of reinforcing fibers and a resin matrix. And there's 3 types of reinforcing fibers that you can use. You can use aramid, carbon, or glass. And in this study, we're looking at using the glass fiber reinforced polymer. And it is a substitute for steel. It is non-corrosive, and it's got some pros and it's got some cons. The pros are it's non-corrosive in a salt environment. It has a very high strength to weight ratio, high tensile stress, it's non-magnetic, and it's low thermal and electric conductivity. Those are the pluses. The minuses are it's got no yielding before brittle rupture, low modulus elasticity, and right now it is expensive to manufacture. The other issue that you have with fiber reinforced bars are you can't just take and bend it into an S shape like for a stirrup, or if you wanted to make a hook. What you actually have to do is during the manufacturing process of the bar, while it is still molten, then they will bend them into the required shapes. So that's another issue that you have to deal with the FRP bars. Now, to just give you an idea what they are, they're round in cross section, and they sand coat them with helical wrap binding the glass fibers and resin together. In the bottom right hand corner, you can see what the helical wrap is. They are the minimum 70% glass fiber content by weight, and they're elastic and then brittle. And when I say elastic, you can bend them a little bit, but there is no yielding. It's a brittle failure. And you can see in the table below for the two bars that we used, we had a number 5 bar and a number 6 bar. The guaranteed tensile stress is 95 KSI for a number 5 bar and 90 KSI for a number 6 bar. But what you can also see is the modulus elasticity is very low. Just to give you an idea of what type of failure you get, the green line is a normal reinforcing bar. And that you can see goes up. The stress strain curve goes up to 60 KSI, and then you get elongation due to yielding of the reinforcing bar, and you end up with eventually a ductile failure. The stress strain curve for a GFRP bar is a lower slope, so it has a lower modulus elasticity, and you can see that it breaks brittly. There is no elongation. So what happens with this type of material, you have to design everything differently than you would with steel. You have to design it so the concrete fails before the GFRP bar does. So to give you a little history, GFRP reinforcement actually can be traced back to World War II with the expanded use during in the aerospace industry. In the 60s is when it was first considered for reinforcing in concrete, and the first projects funded by the US DOT was in 1983. By the 90s, the Japanese had used it on over 100 demonstration projects. In the late 90s, we can find demonstration projects throughout the United States and Canada. Looking at how you design it, we're looking at the Service Limit State Compliance Design Guides, and you have ASC 318, you have ASC 440, and we're also looking at the AASHTO LRFD bridge design specifications. The last thing is that ACI has come up with a guide for design and construction of structural concrete reinforced with FRP bars, and the AASHTO also has a design guide for the reinforcing concrete decks and traffic rails, and both of those were put out in 2008. So to give you an idea of, these are the demonstration projects that are used around the United States right now and in Canada, and these bridges have been constructed and they're being monitored to see how well the GFRP is working in the decks. Here is a typical cross-section of the GFRP bridge. You can see you've got two girders, and in this case they're pre-stressed girders. You've got your concrete deck, which is approximately 8 inches, with 1.5 inches clear on the top, 1.5 inches clear on the bottom. The transverse bars are number 5 GFRPs at 6.5-inch centers top and bottom. On the top, we're using number 5s at approximately 6-inch centers on the top. And then on the bottom, for the longitudinal direction, they're still using number 15 metric steel reinforcing in the longitudinal direction. So next thing we want to look at is how do we design the bridge decks. A bridge deck is reinforced concrete, and it is a multiple span condition in the transverse direction. In the longitudinal direction, the deck is one continuous plate. So really the deck is supported by large rigid plates at the deck girder locations, which are the top flanges of the plate girders. Then you have concentrated wheel loads applied over an area corresponding to the footprint between the deck and the tire. And this is clearly indicated in AASHTO, is an area that's 20 inches by 10 inches. So how does a bridge deck actually behave under loading? There are really two philosophies that are in LRFD. One is an empirical formula and one is what they call traditional. On the left, you can see the empirical, how it behaves, how the empirical formula in LRFD design specifications is based on. It is based on the strut and tie method, where essentially you apply a wheel load, and instead of that deck wanting to bend in curvature, it actually tries to punch through the deck. And so what happens is the bottom reinforcing in the transverse direction acts as a tension tie, and you have a compressive strut that goes from the point of the wheel load to the supports, which would be the two girders. Now this is the empirical formula, and this is what is used primarily in Canada for their design. It tends to yield lower reinforcing than what you would get with what we call the traditional method, is how we design them in the United States. And that is shown on the right. On the right is the flexural model, where you have a wheel load put at mid-span and it wanting to make that deck curve, where you have a positive moment in the center and negative moments over the supports. And that's the model that we used in our design. So above is what we were modeling. This is a truck going down. This is not totally realistic, because you're not going to have a bridge that's only got 3 girders on it. But what we're modeling was a truck going longitudinally, and you have 3 longitudinal girders, and you have a concrete deck spanning between them continuously. So the way we modeled it was to have 2 wheel loads 6 feet apart, which is what AASHTO requires, and we're centering it on the middle support. And what we were doing with this research was looking at what was the effects of the truck in negative bending over the supports. So based on this, this is how we loaded it, and we go back to that the MU has to be less than phi mn, where MU is the applied load, and that has to be less than the capacity. So based on the MU is the factored load, which is 1.4 times the moment of dead load plus 1.75 moment of the live load plus impact. And that is what the demand is. So calculating this out, we looked at using the LRFD design specifications. The service wheel load is 20 kips per wheel, and this is for an HS25 truck. And the reason why we used HS25 was in the Northeast, predominantly, most of the bridges are designed for HS25 loading and not HS20. The next thing is the other parameter is the wheel spacing at 6 feet, and then the effective impact, which is 1.33. Now, because we have one truck on this, the multiple presence factor depends on how many trucks you have loading. And in this setup, we just have one truck, so we have a multiple presence factor of 1.2. So therefore, what that yields is that our service load is 20 kips times the 1.33 times the 1.2. So that's 31.92 kips per wheel. So now what we have to do also is look at, that is how much load that wheel applies. But AASHTO allows us to distribute that wheel load in the longitudinal direction a certain distance, which is called ES, which is the equivalent slab. So for negative bending, which is the case we're looking at, ES is equal to 48 plus 3 times S, and S is the effective slab span. In our case, we're 8 feet center to center of girders, and then it's at the quarter points of the flanges, and our flanges are 12 inches wide. So therefore, our effective slab is 7.5 feet. And when you put that into the equation, you end up with E sub S is 5.9 feet. So that yields that in a 12-inch wide strip, you're going to have you're going to end up with 5.42 kips per foot of wheel. So the other things that we're looking at are, we're looking at service limit states and fatigue limit states. For the fatigue limit state, AASHTO says that you use 75% of the design service value, and the impact factor is 1.15, and your multiple presence factor is 1. So therefore, for your loading for fatigue ends up being 17.25 kips per wheel, and you divide that again by the 5.9, and you get 2.92 kips per foot along the beam. So those give you the two loading combinations we're looking at. We're looking at service and fatigue. And now let's look at the capacity of the beam. In traditional reinforced concrete design that everybody has learned, you have a reinforcement ratio for steel, and you have a balanced reinforcing ratio, which is the point where the concrete and the steel yield at the same time. So in an under-reinforced for flexure, the steel yields prior to the concrete crushing. In over-reinforced, the concrete crushes first before the steel will yield. Now, in traditional design that we do now, we always do things for under-reinforced because we don't want the concrete to crush. We'd rather sit there and see the steel start to yield and deform and give us an indication that there's a failure coming, so that you have time. As you remember, the steel is going to heat yield and then elongate for a while. That's traditional design for steel. For GFRP, we have to design it the opposite, because remember we said that the failure of the GFRP bars was a brittle failure. So what that meant is that if we load this and we get to the yield point of the GFRP, you're going to have a sudden failure. So what you want is you want to over reinforce it so that when you have it getting close to failure, the concrete is the indicator of overstress, so that you don't get a sudden failure. You start seeing the concrete crack, crush, then you know that you have an issue before the GFRP bars fail. To put things in perspective, these are the bridge studies that were done around the United States and Canada, and you can see the ratio of the road divided by road balanced is all greater than 1, meaning that these are all overly reinforced projects. So let's go through some of our sample details that we came up with. There were 6 samples that we tested. 2 beams with number 5 steel reinforcing to simulate what is actually designed now. 2 beams with number 5 GFRP bars and 2 beams with number 6 GFRP bars. We made the deck 8.5 inches deep, and we made it 10 inches wide, and the 10 inches was to simulate the 10-inch width of the truck tire. So first thing everyone in the lab did is we made up the forms, put the GFRP bars in, poured the concrete, and let the concrete beams cure. We based everything on a PennDOT's AAA concrete mix that was delivered to the lab. We had a slump of 7.25 inches, and they added plasticizer in it to help it move around. The design strength that we were shooting for was 4,000 psi. Well, as you know, concrete usually comes in a lot higher than what you specified, and in this one, it was 133 days before we started doing any testing, and by that time we took concrete cylinders and found that our strength was actually more in the range of 7,500 psi. So with that, we had to go back and take a look at our reinforcing ratios and make sure that we are still okay. So you can see on the table on the right, based on 4,000 psi concrete, what our reinforcing ratios were, and they were in the order of magnitude of 2 with 4,000. By going to 7,500, they were 1.5, around 1.5. We're still greater than 1, so therefore the premise that we're going with, that the concrete is going to fail first before the GFRP bar does, was still holding true. So let's take a look at how we set everything up. This is the test setup that we use. There's a concrete sample. We have 2 loads at 6 feet apart, 8-foot spans, and down at the bottom right-hand corner, or excuse me, the bottom left-hand corner, you can see the sample that we had, and it sat on steel plates that had underneath them load cells, and then we had steel supports to support the ends of it. And you'll see some pictures down the road. On the right, you can see the actuator that we used. It was a 35 kip hydraulic actuator, and it had a plate down in at the bottom of it that was attached to a steel beam that distributed the load in 6 feet to the 2 beams. This is a better picture of what the test setup was. You had the actuator and the steel beam sitting on a W12 by 26. And then those sat on rollers that sat on steel plates that were 20 inches by 10 inches to simulate the contact area of a truck tire. And underneath that, we had a foam pad between the steel plate and the concrete. And the reason for this was just so that you didn't get any stress concentrations between the steel plate and the concrete. Just to give you an idea of all the testing setups that we had a computer program, 3 different types of data collection for all the data that we were collecting. You can see here that we had 19 different gauges or deflection LVDTs or load cells that we were collecting information on. We had the number 1 was the load being applied from the actuator, and that had a load cell inside of it. Position 2 we had one load cell, and then at position in the center span, we actually put two load cells. And at the right-hand side, we didn't have enough load cells, so that we just left that one as a roller bearing. And based on simple statics, you were able to calculate out what the reaction was at that point if you needed it. The next thing that we were collecting data was for the deflections, and these were using an LVDT. And on the right-hand side, you can see what they were. There were 6 of them placed at the different points underneath the beam, and then we had one which was a crack indicator, and that's that picture to the left there, and we'll talk about that in a second. So what we did is we put 2 LVDTs at the points of where the loads were applied, and one of them was a much coarser deflection. It measured the deflections much coarser. It wasn't as refined as the other one. And so what we did is during the initial deflections, we were using the more coarse one to see when we were getting deflections, and then we would pull that one out in case we got a sudden failure. We also had blocking to make sure that if we did get a sudden failure, we didn't damage any of the equipment. We also put LVTs at 0.7 and 0.10, and these were the points where we anticipated the maximum deflections based on our analysis. And the next thing we did is we had concrete strain gauges placed at various locations. We put concrete strain gauges on the sides of the concrete at the bottom, at the center support, and then put concrete strain gauges on top and on the sides at the points where we were applying the load. Additionally, we put strain gauges on the GFRP bars on the top bars, since those were going to be in tension. This ended up being not working out too well because either the bonding that we were doing or there was some issue with the wires disconnecting, because I would have to say on half of them we lost signal. And the last thing we had was an LVDT at the center support on the top, calculating out what the crack width was. Now, we knew that we were going to get cracking at the center line, at the point of maximum negative moment. And we wanted to be able to measure that crack. Now, one way you could do is, once the beam cracks at that location, set up and stop the testing and then install this type of apparatus. But what we did is we actually saw cut across the beam at about 3/4 of an inch deep by an 1/8 inch wide, what we call the crack initiator. So by putting in a sawed cut joint there, we guaranteed that when the cracking first started, that's where it was going to be cracking. And so what you can see here is the LVDT is mounted to the concrete on one side. On the other side, we just put a little angle, bolted that to the concrete. And as the beam deflected, it would measure what that crack width would be. So we had 2 loads that we were looking at. One was, we calculated out before, was the load for service, and that was 5.42 kips per foot. And we're multiplying that by 10/12 because our beam sample is 10 inches wide. So you get 4.5 kips per wheel. And you do the same thing for fatigue, and you get 2.5 kips per wheel. So the MTS, or what the MTS is the actuator, had to, for service, apply 9 kips, and for fatigue, 5 kips, because there's 2 wheel loads. Here's all the different testing that we did. Remember, we said we had 2 steel, 2 GFRPs, and 2 number 5 bars and 2 number 6 bars. And the way we tested every one of these was, first test was under service load, 10 cycles, very slowly. And what this was to do was to say, okay, we're going to put it under service load and essentially break the beam in and let it do whatever cracking it's going to do under a service load condition. Very slowly, just kind of put some load on the beam. The next tests were 3 different tests for fatigue loading. We changed the loading to fatigue loading. We do run 10 cycles very slowly with the fatigue loading on it. Then we go and apply 100,000 cycles at a much higher frequency. And then the last 10 cycles we do very slowly again. And what we're going to do with this is compare what happens after 100,000 cycles. Then we apply the 10 cycles of service load on it, and what this ends up being is a comparison. Test 1 and test 5 are a comparison to see what happens after 100,000 cycles of loading. Has there been a reduction in strength? And test 1 and test 5 give us those information. And then the last thing we did with test 6 and 7 were we wanted to fail the section. So this is the loads that we had. We had the uniformly distributed, or we have your uniform distributed weight of the beam, and that ended up being like 91 pounds per foot. We also had to take into account the loading apparatus, which was about 550 pounds, and put all that into our equations to figure out what is our shear and moment diagrams going to be under service and fatigue. And what you have here is what the 2 different diagrams are. So let's have a discussion about what the test results were. We're going to look at how the thing cracked, what the effects were for 100,000 cycles, look at service limit state compliance, fatigue limit state compliance, and ultimate capacity and strength compliance. So first, let's look at how in the world things cracked. This is the 2 steel samples we had. And you can see the pictures that you see are at the completion of test 1, test 5, what the cracking looked like. And now I'm going to go through with a diagram and show you what the cracking was. So the test 1, which was the 10 cycles service load, after that you saw in both samples just a little bit of cracking in the negative over the center support in the negative moment region, which is what you would expect. At the end of test 5, which was after the 100,000 cycles of fatigue loading, you can see the steel started, the crack at the center started extending a little bit more, and there were cracks initiating at the bottom of the locations of where the load was applied. In the second steel one, really didn't see any increase in the cracking. After test 6, now you can really start seeing some cracking initiating on both of them. For sample 1, you see the cracking coming up from the positive area, and you see the negative cracking starting to extend. In sample 2, you could really see the cracking now extend in the negative and positive moment regions. And in test 7, where we finally got what we want to call failure, because we were not able to fail any of these to the point where you had a big failure of the beams. There just wasn't enough capacity in the actuator for it. But you can see the cracking patterns. You have flexural cracking on sample 2 here and here, and you actually have a shear fracture at near the support. So let's take a look at the GFRP bars. How did they react? At the end of test 1, you had cracking, much deeper cracking at the negative support on sample 1, and you started seeing cracking at one of the locations, underneath one of the locations of load in the west side. After 100,000 cycles, you really didn't see much more additional cracking. And now we're loading it to failure in test 6, and you can see the cracking that was exhibited. A lot more cracking in the positive area. Those are flexural cracks. And again, you can see what looks like shear cracks developing at the negative moment area. You have the flexural cracks here, but now you have diagonal cracking essentially coming from the load going to the points of support. And test 7, we just saw an increase of the length of all these cracks, but nothing substantial failures. For the number 6 bars, we saw a lot more cracking under the first phase, under test 1. Then when we went to test 5, you saw an extension of the cracks, but no additional cracks were forming. Under test 6, you can see how we got more cracks in the negative region and a lot more flexural cracks. Again, you can see flexural cracks here, diagonal cracks here. In test 7, just saw an extension of all those. So let's take a look to see what happens due to the 100,000 cycles. So what you're going to do is compare the last cycle of test 1 to the first cycle of test 5, because within that range was test 2, 3, 4, and that's where you were loading it to 100,000 cycles with the 100,000 cycle load. So by looking at the stiffness in the area of the hysteresis loop, we can get an idea of what the effects were. Just to give everybody a little education, the area enclosed within the hysteresis loop represents the irreversible energy of deformation that occurs due to a crack width formation and to a degree of creep. So that area there inside here represents the loss of strength. What you have is your stiffness, and your stiffness is the slope of this line from the minimum load to the maximum load and what your crack widths were or deflections. So first thing we're going to look at is the steel sample 1, and we're looking at crack width. And you had 100,000 cycles. The black line is the last cycle of the first test of the service, and the magenta line is the first cycle of test 5, which was the first one of the 10 cycles of service after we ran the 100,000. And you can see that the slopes are pretty much the same. For number 5 GFRP, again, you can see the black is the last test of test 1 and the magenta is the first test of test 5. And again, you can see that those slopes pretty much haven't changed. And for the number 6 bar, we have the same information. So what does this tell us? the steel, if you look at the change in slope, was minus 3.6% for the steel, 2.7 for the number 5 bar, and 4.9 for the number 6 bar. So you had a change in deflection, a change in stiffness, but it was actually, the slope didn't change too much, so it wasn't that bad. So also the thing that this is telling us is that the GFRP bars change in stiffness is the same, relatively the same as the change in stiffness that we got in steel. So the magnitude of the area of the hysteresis loop decreases with an increase in the sample's stiffness. And so you could see that the energy for the steel divided by the ratio of the steel to the number 5 bar was 0.14, and for the number 6 bar was 0.21. So relative to the steel, the GFRP has a lower percentage in change in crack width energy. So let's take a look at the strain. And you can see through here that on this one we had the black bar is the last cycle of test 1. And then that's the rebar on the north side. And the green is the last cycle of test 1 on the south side. But then we only have the red one, which is the first cycle of test 5 on the south. We lost the north rebar. So you can see again, as you go from comparing the green one to the red one, you can see that the rebar starts getting a little bit, the stiffness decreases after 100,000 cycles. So looking at the last test, and the ratio of the steel to the number 5 was 4.5, and for the steel to the number 6 it was 2.8. So in looking at the graphs, you can see that the loss of stiffness for the steel versus the number 6 bar was primarily about the same. Number 5 bar we really couldn't make too many conclusions on because we'd lost some information, and because of the failure of some of the stress gauges. So here again we're going to look at the energy, and you can see that number 6 is in good agreement with the steel samples, but again we kept losing the bond between the strain gauge and the GFRP bar, so we lost a lot of information here. The next thing we want to look at is at the load points, how much deflection we were getting. And if you compare the black and the magenta, you can see that after 100,000 cycles, the curves almost fall right on top of each other. So what that is essentially telling us is that there's very small changes of the stiffness of the member due to the 100,000 cycles, because of the fact that at the load points, you're deflecting the same, almost the same as if you were without the 100,000 cycles. And again, the change in energy is largest for the number 5 bar at the numbers at the east point. We had a lot of issues on again with data collection, so there's some information that doesn't 100% jive here. So now that we've got all this test information, we want to talk about how does this relate to service limit state compliance and then fatigue and ultimate. So first we're going to look at the service limit state compliance. You have to look at crack width, deflection, and material strains. So the allowable crack width under service from AASHTO and from ACI is that for steel, your allowable crack width has to be less than 0.012 for steel and 0.02 for GFRP. Looking at AASHTO requirements for deflection, we're going to base this on L over 1,000, where L is equal to 8 feet. And that's the same whether it's GFRP or steel, and that's 0.096 inches. And the last thing we're looking at is the allowable concrete strain at the service limit state. So the maximum allowable concrete strain is equal to 0.45 F sub C prime divided by the modulus elasticity of concrete. And we're using the 4,000 for the design compressive strength because that's what we're designing for. And based on that, it has to be less than or equal to 499 microstrain for steel and GFRP. So let's look at the number 6, the first number 6 bar. And you can see that this is tests 1 through 5 are the blue, and then test 6 and test 7 were the ones that we were taking it to failure. We're looking at allowable crack width at the present moment, and so in the black is the allowable limit state at service, which is 0.02 inches. And the measured value at service is here, and that was 0.016. The solid green bar at the top is the flexural capacity that we calculated out, and the green line down here is the shear capacity. So you could see the requirement was 0.02, but we were getting a crack of less than that. The other thing you notice here is both of these tests, we tried to fail the beam completely, and we were not able to because we had to stop the test because we had reached the capacity of the actuator. Taking a look here for the second sample for the number 6, you can see again that the requirements, we had to be less than 0.02 inches for GFRP, and our measured value is 0.017. So looking at everything, we'll see that if you look at the ratios of measured versus allowable, you want all those to be less than 1, and you can see for the steel, we were less than 1, meaning that we are less than the allowable, and for the GFRP, we were in compliance with the service limit state crack widths. And the next thing we want to look at is the allowable deflections. We show the same type of curve. Now the difference is here is the allowable limit is down here, which is the 0.096, and this is for number 5 GFRP bar, and this was on one of the east side LVDTs, and this is the maximum deflection point, and you can see our maximum measured that we ended up with was 0.089. So again, we're in compliance. Again, you can see as we were trying to take this thing up to failure, we got it past the point that we calculated out what the flexural capacity was, but still we're not able to break the beam. Here is another number 5 bar, GFRP bar, and there again you can see that the allowable is 0.096 and the maximum measured value was 0.072 at service. So in summary, we'll show a table here, and you can see that the ratios, we had LVDTs on the west side and on the east side, and you can see that all the ratios except for one were less than 1, and we had at one location where we had it just over 1. So pretty much after 100,000 cycles, you can say that it had you're still within compliance for allowable deflection. Let's now we're going to look at the concrete strains, and this is for the steel sample. We're going to look at the gauge on the north side of the concrete, and again, the measured value, the allowable was 499, and here our measured value was 243, so we're in compliance. For the second beam that we had steel reinforcing in it, we were a little closer. We had 436 microstrains, but we're still within compliance. And now once we go to the GFRP bars, now we had some non-compliance. Looking at the number 5 and looking at the gauge on the south side of the concrete, you can see with the magenta line here that we're actually at 580 microstrains, which means that we're over capacity. For the second one, we're at 347 microstrains. So you can here's a summary of all the ratios, and this is the concrete strain at the center of the sample, essentially at the center support at the bottom. The allowable was 499, and you can see that the ratios, some of them are below 100, some of them are above 100. There's one that's outlier that's 1.98. You know, taking a look at this is nice information to have, and it shows pretty much that we're in compliance, but a lot of it has to do with where the gauge was, how it was put on, and what effects that we had with how we loaded everything. So we looked at this information. Yeah, we had some issues here, but I think you take this into combination with the deflection and the crack width, and those are going to be more indicative of our compliance. So we're going to look at fatigue limit state compliance, and we're going to look at here material strains. So under fatigue for the steel, you had to be less than or equal to 762 microstrains. For the number 5 bar, it's GFRP bar, it's 2,247, and for a number 6, it's 2128. So looking at a number 5 GFRP bar, the allowable rebar strain, we measured 1063, and the allowable is 2247. The one thing that we should note on this is once we started loading this thing up to failure, we lost the communication with the data acquisition. This may be that either the wire inside the sample came loose, or somehow the strain gauge became damaged. Here's the other number 5 sample that we had, and you can see again that our measured microstrain was 680, and the allowable was 2247. Again, you can see as we tried to load this thing out, we lost signal on the strain gauge. So as a summary of what we had, the information we were able to get, you can see that the measured divided by the allowable was well within compliance for strain on the rebars during the limit state, the fatigue limit state. We have to try to figure out a better way of bonding these strain gauges to the rebar without damaging the rebar. So that is one thing that we're looking at right now. So the last thing we want to look at is the ultimate capacity and strength compliance. So as we talked about before, the factored load is given in the equation 1.4 moment of dead load plus 1.75 moment of live load. Calculating that out with the information that we have, the applied maximum factored applied load was 13.4 kip feet. So now we're going to look at what the design strength is. So calculating out Phi-Mn for a GFRP bar, we're going to look at force equilibrium to solve for the ultimate capacity of over-reinforced RP sections. The tension forces must equal the sum of the compressive forces. You have this equation here where the moment capacity is the tensile force in the rods, the bars, and you have the D minus C plus the compressive force times the D minus G, which we'll show you in a second. So that is the equation from the design guides on how to calculate out the capacity of a beam with GFRP reinforcement. Now, it should be noted that the phi factor for GFRP is 0.65. For the under-reinforced steel section, only the tension reinforcement was considered. So therefore, your M sub n is equal to the area of steel times the yield stress times the sum of D minus A over 2. And for steel, your phi is 0.9. So calculating out for your steel, your phi sub m n is 17.67 kip feet. And for the number 5 bar, it's 16.68, and number 6 bars is 18.56. All of those are greater than the 13.4. So all the samples comply with flexural capacity. The next thing we wanted to look at is the shear capacity. And the shear capacity is the same load factors, and we end up with FU has got to be equal to, or ends up equaling 7.3 kips. So in a slab, we're calculating out only the resistance of the shear of the concrete in the beams. There is no shear reinforcing. So the contribution of the shear resistance of the concrete above the neutral axis, the interlock of the aggregate, and the dowel action of the longitudinal tension reinforcing are all what gives you your shear capacity. So for steel reinforced, it's 2 square root F sub C prime times the width times the depth to the steel, centroid of the steel. That is the shear capacity of the concrete. And we have a phi factor of 0.9 for steel. For GFRP bars, you have a phi factor of 0.65, but now you have a V sub C is equal to 5 times the square root of F sub C prime, B, which is the width, and then C is the concrete transformed section neutral axis depth, KD. And you can see below how you figure that out. So the V sub U has got to be equal to less than the V phi n, and the V phi n for steel is 10.42, but for the GFRP, there are 2.7 and 3.1 respectively. So this is what the code is asking you to design for. But as you can see from our results, we were putting a lot more load on the sections, and we did not get a failure of the concrete and shear. We ended up with cracking and apparent shear failures, but did not get an actual failure where the section dropped, where you had cracking and you couldn't take any more load. So looking at the capacities, or looking at for the ultimate capacity, you can see that the dashed line was the shear capacity, the solid green line is the flexural capacity, and you can see that we took the actuator almost up to the 35,000 pounds. On one of them, we really pushed it, and to see if we could get to failure, and we didn't get to failure with any of the steel ones. The number 5 GFRP bar, you can see that the solid green line is at about where that is, about 32,000 pounds, and the failure for the shear is like at 8,000 pounds, and you could see that we were able to load it much higher than that. And the same is true with the number 6 bar. So what we wanted to look at was converting our phi sub n to a load on the MTS, and the MTS is the actuator. So the P MTS is the corresponding load to the shear capacity. So we ended up with the shear on the of 450.455 kips, and then you had the shear of LA is 0.22 kips, and we're going to set the MTS at 1 kips. So the shear, the center support corresponding to 1 kip of load is 0.41 kips. And we're converting the moment the same way. And so for every load, every kip you put on the actuator was equal to 0.76 kip feet of moment. So by doing this, you can see that the actual load on the MTS far exceeds the shear capacity. For the steel, our predicted ultimate limit state was flexure, and for the 2 RFP bars, they were shear. So we predicted, you can see what we predicted what the capacity was versus what we actually measured, and you got a ratio. For the steel, we're about 1.5 more than we predicted. But you can see for the GFRP bars, the failure was supposed to be in shear, and we got 4 times the capacity for the number 5 and 3.5 times the capacity for the number 6. So what that's kind of telling us is that for the GFRP, the failure model was more the tension strut that we see on the left. And it wasn't necessarily a shear failure in the terms that we are thinking of. It is actually, you're creating a model here with a load coming down, and you had the GFRP bars acting as a tension rod, and then you had a compressive strut being formed. For the flexural model, it was more what we look at for our traditional design. So what we want to look at is ACI 318 section 10.7 says that compressive struts should be considered in deep beams. And what are we looking at as a deep beam? Well, the clear span is equal to or less than 4 times the overall depth of the member. So 8 feet or 96 inches has to be greater than 8.5 times 4 or 34 inches. So it doesn't solve or doesn't agree with, but the concentrated load is within twice the member depth from the face of the support, or 36 inches or 17 inches. So for both of those, we really can't consider it a deep beam. So what we're looking at here, that's if you look at what the point load is. But now if we actually take into account that these plates were 20 inches wide, now you set, and your plate at this plate was 20 inches wide, this plate was 17 inches wide. So now your distance goes from, your distance is 36 inches, which is the distance from here to here, minus the 7 inches, minus the 10 inches, which is 19 inches. So now you start seeing that the load, this is a very stiff plate distributing this load, and this is a stiff plate. This is the distance. And so, you know what? Now we're looking at it being acting more like a deep beam. So the other thing we wanted to look at with the two beams here is now we have a tension strut here, and we still think that because of where the plates are and everything else, that this is acting more in ultimate failure as an arch model with compressive struts and ties than a flexural model. So what kind of conclusions can we make? First thing we can do is say that the performance of GFRP bars before and after 100,000 cycles is equivalent to steel. You're really not losing a lot of strength, and it's behaving the same way as steel would. There is no trend suggesting accelerated stiffness or energy loss from fatigue loading. And the measured crack width and deflection for GFRP are all within the allowable limits. Now, we did notice that several of the concrete strains exceeded the allowable limits, but there may have been some residual stresses from previous tests, so we can't tell if those were due to the loading or if they were residual stresses. And the last thing is that the measured GFRP strains are all within allowable limits. Analytically, the GFRP sections satisfy flexural strength requirements, but the GFRP fails the shear strength requirement if you look at analytically. But we realized from our measurements that the capacities were 3 to 4 times what we predicted based on the formulas. This leads us to believe that the formulas, more testing has to be done for the shear capacity because you're getting more capacity than is actually there. And one of the other things that we concluded was that the beam model is a poor method of analysis for negative bending on GFRP reinforced bridge decks. Arching action appears to play a significant role in distributing the wheel loads through a deck. So the test results conclusively show GFRP is a viable alternate for steel and reinforced concrete bridge decks for the load cases considered. And this statement is made in reference to the effects of the fatigue loading, service compliance, and the service and fatigue limit compliance. Future work that has been done at Villanova that we have not published yet is part of my work on my PhD. We actually took more of these samples that we had and ran a 2 million cycle study. We also looked at, and that was for negative bending. We also looked at the positive bending case where we moved the truck over so that we were loading it for maximum positive bending. And the last thing that was done just a few years ago is we actually built sections of bridges in the lab and looked at two-way slab action, because a concrete bridge, what we modeled with our tests were a 10-inch wide beam, and we looked at it as a simple beam. But in actuality, when there's a load case or load put on a bridge, it acts in two-way deflection. So those were results that were done by some other students working on their masters. So just to give you an idea of what we had, you can see this is the actuator, this is the steel beam, that's the steel plate that we had pressing on the beam. And you can see here we're just setting up to put the load on it. We have cinder blocks here with wood that we were pulling out wood as this beam was deflecting. So we didn't want, if there was a failure, we didn't want to ruin any of the expensive LVTTs. Now you can see this is a number 6 GFRP beam, and now you can see the crack patterns that you can see. Here's the diagonal cracking, and you can also see some of the curvature under that this beam is under due to the loads. Now, this is one of the failures that we got, and you can see that it's a shear failure from here up to where the load is. And then there's the GFRP bars never failed. It was the concrete that failed, but it didn't fail really in compression, it failed more in shear. And this is a number 5 GFRP bar that we got it to fail. Now here you can see just a idea how flexible and how much deflection that we were getting with these samples. This is with the number 5 GFRP bar. And again, this is a failure that we got on one of the samples where it's again failing from that plate to that plate, and the GFRP bar held together very well. We had a heck of a time just cutting these apart. Now, as I said, that we did some additional testing for positive bending, and you can see now where here's the wheel closer to the center, and we put this more at the point of positive bending where we're applying the load. And here again, you can see what the failure was. And this was just an accident that we had when I was working on my project. Those actuators are very sensitive, and if you type in the wrong thing, it'll do exactly what you tell it to do. And I meant to move it, the actuator 0.01 inches, and I said 1 inch, and it drove the actuator and the steel beam and everything in and failed it right away. And fortunately, nobody got hurt, though the steel load beam W12 by 26 went flying across the room. So I'd like to thank everybody for listening to this presentation, and if there's any questions, I'll be free to answer them now. Thank you.
Okay, so we don't have any questions so far, but if anyone wants to go ahead and type some in, feel free to do that. We'll give it a minute or so.
Okay. I guess I put everybody to sleep.
Okay, yeah, looks like we don't have any questions today, but Zane, is there a good email they can reach you at, or would you like them to go ahead and email me if they have questions
Why don't you just have them email you and then you can forward them to me?
Okay, everyone, so my email is Ariana, A-R-I-A-N-A, @frontlineco.com if you have any questions to follow up with Zane. I just have a few more announcements before we sign off. Just a reminder, like I said earlier, There won't be handouts for this presentation, but you can find the quiz at the same link. Should be in your confirmation email from this morning. I just want to thank you, Zeyn, for a great presentation. I want to thank everyone else who joined us today. We're going to go ahead and post this on our website for purchase by next week. So if you know anyone else interested in purchasing the webinar on demand, that'll be available by Monday. We also have the other SE Bootcamp webinars available on demand on our website now. Please complete the quiz by this Friday. And I think that's it. So thank you again, everyone. Have a great Wednesday.
All right. Thank you.